start again. I'd like to welcome you to the August meeting. And tonight we'll be getting a presentation from the gentleman over at CUAVA, Professor Cairns and Tony Monger, of the effect of solar activity on low Earth orbit spacecraft. Oh, tongue is getting tired.
Right. Well, I think you see the screen
Yes.
for us. And so, yes, so this is work that that Tony and I have done in conjunction with two students primarily, Vanathi Arid-Selvan and James Lee. And some of you who were at the Australian Space Research Conference last year would have seen the presentation that Vanathi led. And that that work underlies what Tony and I are going to present today. And she did an excellent job. But one thing that Tony and I are doing is revisiting some of the analyses. And so you'll see some of the fruits of that reanalysis today. But as the title says, we're looking at the effect of solar activity and, in fact, more generally, space weather as a whole on the orbits of satellites around the Earth. And we'll focus entirely on one satellite, the CUAVA-1 satellite, which is the satellite that the Australian Research Council Training Centre for CubeSats, UAVs and their applications, otherwise known as CUAVA, put into space about, it's been now about 1.75 years ago, and it re-entered approximately 3/4 of a year ago. Unfortunately, radio silently, and it was radio silent the whole time. So one of the things, so we had essentially a dead spacecraft in space, and we wanted to try and get some science out of it. And independently of what we wanted to do, NORAD and various other groups use radars to establish the orbits of satellites. And so we wondered whether there would be effects on the orbit of the satellite due to space weather and solar activity. And that's what this presentation is about. And Tony and I are going to switch off back and forward, or do a tag team, is another way of putting it, to do this presentation for you. So you can see the aim there. It's to better understand how variations in space weather, driven usually by solar activity, affect the orbit of satellites. And we'll be looking only at one, CUAVA-1. And I forgot to change this. It should say that its initial altitude was approximately 425 kilometers, not 405. Deployed just a few days before my birthday in 2021, and lasted about 1 year in orbit. We entered just about the start of December in 2022. And one of the things that's interesting here is that it was a relatively quiet phase of the solar cycle, which we'll show a little bit of evidence for. And that's interesting because there are potentially, at one time, there might be 2 or 3 active regions on the face of the sun pointing at the Earth, and there might be a number of coronal mass ejections moving their way towards us, so therefore driving various effects in Earth's atmosphere and ionosphere. And so one good thing is that we were launched during a quiet time of the solar cycle, and so we might hope to disentangle the effects of the radiation, such as X-rays and ultraviolet emission, in heating up the atmosphere and puffing it out, and then our satellite going through that puffed up atmosphere and getting higher drag, and so starting its orbit dropping quickly, versus the effects of other space weather events, which we'll talk about. So now I think this is up to you, Tony. I think but perhaps I'll say that we have three parts to this presentation. This next part is going to be primarily, I think entirely Tony. He's going to be talking about orbit theory. Then we'll do a little bit on what space weather is, and then we'll do a bit on the analyses that we've done on the CUAVA-1 satellite's orbit as a function of space weather. And we'll show some really nice evidence, I think, that space weather events are actually affecting the orbit. And you'll see some beautiful just plots of a number of quantities showing by eye effects. Then we'll show a little bit on the power spectrum, showing that so many of these events occur periodically and that the periods are the same approximately for the changes in the orbit and the various space weather events. And then we'll look at correlation functions that try to establish the connection between what's happening to the spacecraft and what happened in space. So that's the plan. So Tony, take it away, please, and tell me when to click.
Okay, right. Thanks, Iver. Yeah, so what we're going to talk about today involves the listener having a bit of a knowledge about how orbits work. Now, it's a long story, but orbits are a little bit more complicated than you think they are. The spacecraft doesn't just go round and round, particularly in low Earth orbit, and that's really why we're able to do this analysis. We did actually some time ago look at other spacecraft, specifically the space station, and the space station showed, and you'll see this during Iver's section of the talk, the space station showed significant variations in the speed of the spacecraft as it travels through the upper atmosphere, because it's such a complicated shape. But the great thing about CubeSats is that they're a very simple shape, and so they have a very, very simple drag profile, and it's easier therefore to analyze. Okay, so to begin, are you all sitting comfortably? Right, the Keplers Laws of planetary motion. Now, this is going back somewhat, and we sort of vacillated or discussed slightly among ourselves whether or not we should present this, but we wanted to bring everybody along in this discussion, and so we thought we'd start from the very beginning, like Julie Andrews did. So that's what we're going to do. So now, in a long time ago, around about 500 years ago, Johannes Kepler, an Austrian mathematician, discovered 3 laws of planetary motion as a result of the data collected by the Danish experimentalist Tycho Brahe. And he came up, he reduced the data using an enormous amount of mathematics, and it was an enormous amount of data. It had taken more than 20 years to collect. And what he came up with 3 basic laws, which are deceptively simple when you consider the complexity of all the data that he must have had to reduce to be able to arrive at these laws. Interestingly, Isaac Newton used these results to derive the law of gravity. So they were very important for a number of things, not just for our ability to analyze orbits, but also for our understanding of more basic physical phenomena going back hundreds of years. So anyhow, the first of the laws is that all orbits are ellipses. A circle is a special case of an ellipse, okay? So what is an ellipse? It's the shape that you see on the screen now. It has 2 foci. The primary, that's the object being orbited, the sun in our case, where there's a planet involved, will be at one or the other of the 2 foci. It doesn't matter which one. And the other foci will be empty. The closer together those 2 foci are, the more circular the orbit becomes. When those 2 foci join together and form a central point, it's a circle, but that's really only a special case of an ellipse. Okay, so that's really the first thing. All orbits are ellipses. Thanks, Eva. The next one. Right. The second law is a little bit more complicated. If we draw a line between the primary, which is the sun or the planet, whatever it is, to the orbiting object, we refer to that as a radius vector. It's just a straight line, that's all. If we calculate the area swept out by that object, by that radius vector, in a certain length of time at any point around the orbit, and then at another point in the orbit, further away, say, if we do that again, as long as the time interval being considered is the same, the areas swept out by the radius vector will always be the same. And what this really means is that the spacecraft, when the spacecraft is at a long way from the primary, from the planet or the sun, it travels more slowly, and when it's nearer to the primary, it travels more quickly. And I think you can sort of intuit that. It's sort of if you can see, it sort of goes round and then slowly and then round quickly through the close approach. Now, the next, there's one more law that I'm going to explain, and then we're going to explain a certain amount of jargon, unfortunately. The third law is a little more complicated, and that's that the ratio, there are two distances from that the satellite has from the Earth. One is the farthest distance, called the apogee, and one is the closest distance, called the perigee. If you take the ratio of the cube of the apogee, that's just a distance, and you divide that by the square of the period, which is the time taken for one complete orbit, what you get is a constant number, and that depends on the thing that you're orbiting, the planet. The number you see on your screen there is the number which is you get when you're orbiting Earth. This derives from Newton's law of gravity. Well, it wasn't derived from Newton's law of gravity. It was actually one of the things that Newton used to derive the law of gravity, but you can also go backwards. And that's what we've done here. So that's a very important point, because some of the data, in fact, almost all of the data about the orbit that we're dealing with here comes from a set of orbital elements, or we call them Keplerian elements, after Johannes Kepler. But in order to understand them, we have to understand what the three laws are, which we've now covered. Then we have to do a certain amount of understanding of jargon and of numbers and so on and so forth. Thanks, Iver. And so this is what we've got. We've got an orbit and we've got a reference plane. You'll notice that in the grey that there's a reference plane noted here. In the case of orbits around Earth, that reference plane is the equatorial plane. Okay, so if you draw a plane that cuts through the center of the Earth where the equator is, that forms a plane. There is similarly a plane surface caused by the orbit, or described by the orbit itself. And both of those are centered on the center of the Earth. So is and the orbit is, of course, also centered on the center of the Earth. As long as the spacecraft is very small in comparison to the size of the Earth, obviously a CubeSat is very small in comparison to the size of the Earth, the two planes are centered on the same point, and we can reference a few details about the orbit from those two planes. And the first of them is that you'll notice that the two planes intersect through the middle, and they describe a line where they intersect. And the intersection goes from what is described on the lower part of the drawing as an ascending node across to the other side of the orbit, exactly half an orbit later, which is called the descending node. The ascending node is the point where the spacecraft travels from the southern hemisphere into the northern hemisphere. Okay, so remember that point. The arrangement, the alignment of this ellipse is described in terms of the latitude on Earth over which the ascending node appears. Okay, so that plane can rotate, or precess is the term they use. And this is one of the numbers that we use to analyze the spacecraft. Another is what's called the inclination. You'll see in the green, the darker green ink there next to where it says ascending node, there's a small arrow indicating a line, an angle, which is the angle formed between the plane, the reference plane, the equatorial plane in this case, and the plane of the orbit. We call that the inclination. The inclination is determined more or less by the deployment from the space station. So the space station is in the inclination, it is about 51 and a bit degrees. And because the spacecraft we're talking about here, CUAVA 1, was deployed from the space station, it has no propulsion of its own, it will also be in that inclination, and it will stay more or less in that inclination throughout its entire life. There is a couple of other points that we need to note, the things called the true anomaly, the argument of the periapsis, and a couple of others. Don't need to worry about those too much. One thing we do need to know, though, is what's called the mean motion. If you could just move on one, thanks now, Iver. And we'll explain that in a moment. Now, the next thing we need to know is, how do we define an orbit? What is called NORAD, but is now known as Space Force, thanks to the former US president, occasionally referred to as the Orange Moron, do a radar analysis of all objects, or many objects, but I think something like 20,000 objects every day. And between 1 and 3 or 4 times a day, they analyze the position of every object, and then they produce a series of numbers called Keplerian elements, or KEPs for short. And then they record, and then they update these all the time. And these are recorded all the time and kept in by an organization on a website called Spacecraft. And we go to that for those. When we do is we download all of the entire set of Keplerian elements throughout the entire life of the spacecraft. And that's how we do this analysis, okay? Now, the format that we get these in are called 2-line elements, and that's because obviously they're in 2 lines. You'll see that in a minute. One of the numbers we have to deal with is what's called the eccentricity. The eccentricity is the extent to which the orbit is in an ellipse. The higher the eccentricity is, the more elliptical the orbit is. The lower it is, the more circular the orbit is. Okay, so that's one. Another is what's known as the semi-major axis A. That's the distance between the orbit, the center of the orbit, and the longest distance out to the object. And in this case, you'll see it here. There's a small blue line. Okay, so that's the point of the maximum distance, or the apogee. Thanks, Iver. The next one is the inclination, which I explained. That's the tilt of the orbital plane, which we showed earlier on. And that tells us a few things about the spacecraft. Most importantly, though, is that it remains more or less constant throughout the life of the orbit, of the mission. And the reason for that is that it takes a great deal of energy to change the inclination, and that's an important point. Thanks, Iver. Now, the last of them is a thing called the longitude, or sometimes also the right ascension of the ascending node. That's the position of that point where the spacecraft goes from southern to northern hemisphere. And that describes, as I said before, what's known as the azimuthal orientation of the ellipse with respect to the vernal point. That's a very technical term. It just means that where is that plane of the orbit with respect to a particular point. And then last of all, there's a thing called the mean motion. And the mean motion is the number of orbits per day. That's all it is. So in order to establish what the period of the orbit is, all we need to do is to divide the mean motion by the number of seconds in a day. That's 86,400 seconds. And we know the period of the orbit in seconds. And because of the Kepler's third law, we can then calculate the apogee. That allows us to calculate the altitude of the orbit, because we know the radius of the Earth. And then we can and there it is there, that's the equation. We just rearrange the equation so that T is the subject of the equation, A is the subject of the equation, and T is calculated from the mean motion, and we can calculate the apogee at any moment that there has been a set of Keplerian elements taken. In other words, that there's been a radar scan of the spacecraft. And then we can map the changes in the orbit over time. And Iver will show you that in a little while. You'll see at the bottom there, there's a thing that says TLE and a whole series of numbers. I won't go into the details of those too much here, but if you see next to the number 1, you'll see 49275U. That's the SATCAT number of the satellite, the satellite catalog number, and that is the satellite catalog number of CUAVA 1. This is actually one of the sets of Keplerian elements. The U means that it's unrestricted. It just means that it's not doing anything dodgy. It's not doing anything secret. If you look down to the right-hand side, there's a number 5515. That's just a checksum. The number next to that, 15.5123, is the mean motion. There's 15.5 orbits per day. And then there's a few other details. One of them is what's known as the B-star drag coefficient. If you look directly above that 15.512, there's a number 30122 minus 3. That is what's called the B-star drag coefficient. And that's just a measure of how much drag the spacecraft is experiencing from the solar wind. And we can measure that too. Okay, so that's all there is to that. I think there's one more slide for me, Iver. Just have a look at it. I know that's my bit done, so that's good. So I'll hand it back to you, and Eva's going to talk about space weather now. That's the stuff that affects the orbit of the spacecraft.
Okay, thanks, Tony. So what does space weather mean? Broadly, it's the conditions in space that may affect human systems and activities on Earth and in space. So it's things that relate to, for instance, solar activity. So X-ray flares, ultraviolet flares, coronal mass ejections moving out through the solar wind towards the Earth. Here's a snapshot which shows what turns out to be a coronal mass ejection moving out. But in general, but it also includes things that are responses in the Earth's magnetosphere. That just means the region controlled by Earth's magnetic field, in the ionosphere, the atmosphere, which means it's neutral, all the way down to the ground. So it's how activity here on the sun and in the solar wind interacts with the magnetosphere of the Earth, and leads to activity that affects, for instance, satellites, might be the electricity grid, all sorts of different aspects that are important to our everyday life, or the motion of satellites. So they're almost all driven by solar activity, and they range from tiddly or really small to ones like the Carrington event that, if it occurred today, could severely disrupt our modern technological society and essentially drive us back to perhaps not the Stone Age directly for the Carrington event, but at least to a pre-electricity age. And as you can imagine, that would be catastrophic for most people alive today. And we need in general to be able to predict and mitigate at least the large space weather events. Sorry, let's keep going here. So let me just show you some of the evidence for the sun and activity varying with time. This is meant to be a movie. Here we go, I think. So what this is and there might or might not be music for you to hear. This is from the Solar Dynamics Observatory. And it's just it takes snapshots all the time of the sun, points there all the time, and look at all this activity, these variations. These are magnetic field loops. See the nice, beautiful, curved magnetic field regions. These are active regions. You see the disk over here with other things happening. So it's really, you look at the sun, most of us with our ordinary eyes, of course, just see something, assuming we have a filter on and we can look at it, that is constant with time. That's not the case. The sun actually varies dramatically with time. But let me not belabor that. Happy to come back to it, but let me not belabor it. Come on. So let's look at more at a cartoon, basically, of how much space weather on the Earth occurs. It's associated with a coronal mass ejection, which is essentially a large explosion on the sun, which reconfigures the magnetic field lines and leads to a large blob of plasma, which is just an ionized gas, moving out from the sun at a speed of order 1,000 kilometers a second. Takes between 2 and 3 days to get to the Earth, and it can lead to significant space weather, such as energetic particles raining down on the Earth in the polar regions and the aurora. So let me show you this, this movie. So here we see.
You all right, Morris?
Here we see the sun. We're going to see
It's a very
coronal mass ejection over here. Here we see the large blob of plasma moving towards the Earth, which we'll see in a moment. We'll see the magnetic field lines of the Earth. We have a process called magnetic reconnection, which occurs here, flips the field lines back, and eventually leads to reconnection in this region here. And energetic plasma streams down towards the Earth and interacts around the auroral zone here and over the polar cap. And this is due to energetic particles coming in and hitting the atmosphere. So hitting ions and atoms and molecules in the atmosphere. So there's a substantial amount of heating there. And you might expect when things are hotter, they're able to move, or that means they're moving faster, they're able to move further away from the Earth. And so the atmosphere puffs up, and then as a spacecraft moves through it, it sees a larger, a more dense material, and it has larger drag. So let's go on. I'm just going to, well, okay, I'll say a little bit about this. There have been very large space weather events in the past. One of the big major ones was in 1859, so-called Carrington event. It had the auroral zone, which is normally around about 65 degrees magnetic latitude, moving all the way down to 23 degrees. So we saw the aurora in places we shouldn't have. Lots of fires from large voltages and currents induced on telegraph wires. And there's a prediction that if that occurred today at the same time, would have taken out the US East Coast power grid for up to 10 years. And the transformers can be destroyed in a large geomagnetic storm like this, and the replacement cost plus the cost of the electricity not sold is anticipated to be of order $1 to $10 trillion. And when you consider that the Iraq War, which arguably at least partly beggared the United States, cost a couple, of order $1 trillion. This is a really major thing. Similarly, that's about the cost of the changes in economic activity associated with the global financial crisis. So very large economic impact. And it's not things that occur once every 100 years necessarily. In 2012, we missed one by 1 week because the Earth was in a different location relative to the sun, that 1 week later we would have been in the path. So these sorts of things are important from the point of view of our modern society, in terms of the electricity grid, communications, GPS, communications and position, navigation and timing, but they're also important for drag of satellites. And I'm just going to skip over this. So what are we going to look at? We're going to look at data from various NASA sources, from the GOES-R spacecraft and a conglomerated data set called OmniWeb. And we'll look at a number of measurements, looking in solar ultraviolet radiation, the so-called MG2 index, X-rays, also from GOES, which is in this sort of range, 1 to 10 angstroms. Look at the 10.7 centimeter radio flux, which is a somewhat poor marker of solar activity, and then 2 that relate to the actual magnetospheric and ionospheric response, which I'll talk about in a moment. There's DST, which involves the so-called ring current around the Earth, and then the KP index, which relates to changing magnetic fields in the auroral zone due to large currents flowing there because of energetic electrons precipitating, just like you saw in the movie, the second movie. So I've sort of gone over that. DST looks near the equator, just measures fluctuations in the magnetic field. KP, it's a more global measurement. And then there's also one called the Auroral Electrojet Index, which measures changes at auroral latitudes. So you're looking basically, I'm sorry for this poor but hand-drawn diagram here. It's a region called magnetopause, which basically excludes the solar wind material and keeps the Earth's magnetospheric material inside. We've got the Earth here. We've got some of the magnetic field lines for the Earth coming out and then going from the southern hemisphere back into the north. Same sort of thing on the backside away from the sun. Sun's over here. So it's a solar wind flow outwards. And there's various measurement locations. And just for those of you who are interested, the ring current is in this region here. It basically looks like a donut, basically, with the axis of the donut being the Earth's magnetic field vector. So those particles basically just move around the Earth. But as they go, if there are more of them, they change the magnetic field measured at the surface of the Earth. Whereas the auroral particles coming in change it over the auroral zone. So you might say, what's the, why do we care about this when we're talking about the CUAVA-1 satellite? And here's something we probably all forget, perhaps. But what we show here is the sun over on the far left coming in, the rays coming in. We've got the Earth's rotation axis at its 23.5-degree tilt. And this is at one particular time. And you notice that if you look at this Tropic of Capricorn here, you can see that the so-called subsolar point, which is the point on the Earth at a given distance closest to the sun, it's down here in the southern hemisphere at the Tropic of Capricorn. So what does that mean? It means that over this region, you have more of the sun's radiation hitting. That's where we'll get more solar ultraviolet radiation that ionizes the atmosphere, for instance, and gives us the ionosphere. Same with X-rays. So we'd see a region here with more ionization, more absorption of the radiation, more heating, more puffing up of the atmosphere in this region here. And then that extra energy will be moved around the Earth by collisions and waves propagating. So that's what I mean by here. If it's the direct solar radiation, then it's going to be a subsolar energy input here, and disturbances from there might then move towards the poles, like this. But if it's energetic particles, they tend to come in around about 65 degrees, basically near the Arctic and Antarctic circles here. And if that's where you get significant energy input, then the atmosphere will puff up here and we'll get disturbances propagating towards the equator. Now, all of us might say, well, why did you show it this way, Iver? This is showing summer in the southern hemisphere. Because we're getting more of the solar input at southern latitudes. But if we moved around in Earth's orbit around the sun so that we were looking at the sun pointing here, you notice that the subsolar point would be close to the equator. And then half a year after December 21st here, so in June, it would be over here and you'd get northern hemisphere summer. So the locations of where the subsolar input would be largest are going to vary throughout the year. But broadly, if it's the X-rays and ultraviolet emission that's important, you're getting most of the energy input close to the equator. If it's the energetic particles and the auroral zone, then it's mostly near the poles. And a question might be, which type of space weather is giving rise to heating and expansion of the atmosphere and an increased drag? Okay, by the way, people are welcome to ask questions. So what are we going to do? We're going to, how are we going to analyze data? We're going to do what Tony said, get the data from NORAD for the spacecraft orbit as a function of time. We're going to get some space weather data from NASA's OmniWeb and the GOES-R satellite, analyze it in various ways, such as just plotting it, detrending it, etc. We'll look at periodicities using a particular technique, not a Fourier transform, because these data, in particular the NORAD data, so the TLEs, are not equally spaced in time. And so that prevents us from using Fourier transform techniques. But we'll see periodicities. And if we want to have an event, a space weather event, giving rise to changes in the orbits, then we'd expect the periodicities of the space weather events and the changes in the orbit to be the same. So that's why we look at periodograms, and then we look at a so-called cross-correlation analysis that we'll talk about. So Tony mentioned this quantity A of T, so the semi-major axis or apogee, or just simply the altitude of the spacecraft, because the orbit's very close to being circular. And the red here is a function of time. So this is starting off at about 425 kilometers. Here's time since the 6th of December in 2021. And you can see this red line, you know, it's not a straight line, right? Or curve, it's not a straight line. There are little wiggles in it, but it's kind of difficult to see, isn't it? But if you look at this standard 3-point derivative, dA by dt, you get something that looks like this, the blue curve. And you might say, well, why does that help you? Well, one reason is because now it's really obvious that, for instance, that something significant happened here. Big change in dA by dt, similar here and here. You magnify the changes in the altitude as a function of time by looking at this derivative. And further from that, what else do you see? Well, you see a variation. You might put a nice line through the average here that starts off pretty flat and then it curves down. So you've got a secular change. You've got some noise. You know, look at these little wiggles here. So you've definitely got some noise, but you've also got these events that look interesting. And so one thing you can do is look at comparisons between dA by dt, which is the blue here as a function of time, and, for instance, the solar ultraviolet radiation given by this Mg2 index, which is this lovely purple one. And you can see the purple one, you know, nicely moving along. It's got peaks every approximately 25 days, as we'll find out. There's a bit of a trend. It's sort of trending upwards, you can see here. You notice that this one here trends downwards. But look, every time we have a peak in this, you know, there's a bit of an event after it in the blue. Bit of an event here. Similarly, a big peak here, bit of an event. Peak here, an event, etc., etc. Peak here, some event, etc. By eye, it looks as though there are some events which relate the changes in the rate of change of the altitude, dA by dt, and, for instance, this Mg2 index. You do the same sort of thing if you want by looking at the drag term that Tony mentioned, B star drag, and that's what this plot shows. And I should have said that these green arrows here are every 25 days. So we'll see a periodicity that's approximately every 25 days in a while. So this is prima facie evidence that there are space weather events affecting Earth's, not Earth's orbit, but rather the orbit of our satellite CUAVA-1. So let's then look at periodicities. If things are correlated, you'd expect them to have the same statistical time behavior. And as I mentioned, we're using Lom-Scargill because we don't have periodically sampled dA by dt data. Basically, that just well, I won't go into that unless someone asks me a question. So what do we have here? This is the power spectrum here for dA by dt in blue. That's in here. Frequency here in units of inverse days. Over here, we have the power spectrum of our ultraviolet Mg2 index. That's the dashed line, the dashed curve here. And you can see that both of them peak at about, 0.04 hertz, which is a 25-day period. 25 is 1 over 25 is 0.04 hertz. I'm just wondering about that. But anyway, it's 0.04 days to the -1. That's what it should be, not hertz. Yeah, there's a typo there, sorry. but got the same periods, so you might expect them to, it's possible for them to be correlated. Is that usual? Here are some of the others. dA by dt with its periodicity, V star drag, same within the error bars, mg2, X-ray flux, blah, blah, blah. Almost all of them have a period of about 25 plus or minus 1.5 days. And they're not inconsistent. One that's different is this KP index. So how do you go further? Well, one way is by doing a cross correlation, which looks like this. It's basically an integral over some time interval, might be from -infinity to infinity in time, of your function f of t here, times g of not t, but t plus some lag tau. So what you're basically doing is lining up your data sets, and then you calculate them when you've got 0 lag. So it's just this product and integral. Then you move this one 1 unit, calculate it again, move it another unit. That's 2 time units of lag, 3 units, etc. So you're just lagging your quantities. And I'm sorry, I don't have a pretty way of showing that. Sorry, here we go. And what we get are these really beautiful results. So this is the cross correlation of dA by dt and the mg2 index. Now this is a preliminary result. This is one of the ones that we wanted to, that Tony and I are wanting to check, because there was some, for the technical people here, there was 0 padding in the calculation, which basically means that the intervals were too long when it was calculated. That's partly why everything goes to 0 at long times. But you notice that it's beautifully periodic. The distance in time between here and here and here and here is very close to 25 days. And you notice that we have a maximum value of this correlation coefficient, about -0.6, which is bigger than the positive peaks here. And it's down at a lag of 3 days. So it's saying here that if you take it at face value, that dA by dt changes 3 days after a change in the magnesium-2 index, or the solar ultraviolet radiation. And this is the sort of thing that you might expect to be causal, as in get a change in solar activity or the ultraviolet radiation that puffs up the atmosphere, and then later on you see a change in the altitude of the spacecraft due to increased drag. But most of us who've done analyses look at that and we say, just how beautiful it is. Just looks as though it has to be right. That's often a dangerous feeling, but anyway. Here's another one that Vinathy, so I should have said this was Vinathy's analysis here. This one here is dA by dt in the F10.7 centimeter flux. Notice again, you've got some periodic variations, about 25 days. And there's much larger negative peak down here, now at negative lags here. And you notice that that peak is significant. You know, if you took the standard level here to be noise at about 0.25 or so, this is about twice as big as that. So looks real. Here's the similar thing that Tony and I have been doing. You notice it looks a bit less pretty. But here we also have a maximum peak close to 0 lags, and it's also a negative lag. So, you know, broad self-consistency, but some quantitative differences. And these quantitative differences are, of course, why we might want to, well, it makes us feel that we were correct to try and revisit things. Okay, Ken. Oh, no worries, Ken. Talk to you later. So let's see where we go. Here we go. Here's another one. This is dA by dt and the KP index. Again, you can see something which in Vinathy's analysis doesn't look very regular in time. but you notice a big peak near 0 lags. But negative lags, again, it's about twice as big as the noise level. And Tony's and my ongoing analysis, again, a nice central peak here, now at positive lag rather than negative lags. And I should have emphasized one aspect here, that when you have a negative lag like this, it means that dA by dt is changing before the F10.7 centimeter flux changes. So you're seeing a change in the orbit before the change in the solar activity that might have been considered to drive that variation in altitude. That is acausal. It's not consistent with causality, in the sense that clearly a change in the satellite orbit didn't lead to a change in solar activity. What we're hoping for is the causal relationship where a change in solar activity changes the altitude of the spacecraft. So in this particular case, we're seeing something that's acausal. It can't be that the solar activity can't be driving this orbital change, or at least not that particular sort of solar activity. This one here with KP, now it's a positive lag, but it's very close to 0, and it's not so far away from this, and it's different from the earlier analysis. Which is correct? Is either correct? At the moment, we're not sure, and that's why this analysis is set to be ongoing. But if we ignore that for the moment, here's Venathi's and our earlier analysis. When we looked at these two, the solar ultraviolet index and the X-rays, we got positive lags, plus or minus 2 days, so almost 0. This would be possible a causal link where we get a change in ultraviolet or X-ray emission leading to a change in the orbit. These ones here, they're all negative though, these lags, and so those have to be acausal. They can't be driving the change in the orbit. So some changes or some solar activity or space weather seems to drive changes in the orbit, and some doesn't. Now, how would we interpret those results? The changes in the magnesium index and the X-rays occurring beforehand suggest that we have a change in X-ray and ultraviolet emission, which is absorbed by the atmosphere and heated and ionized and expands, and that then leads to the atmosphere puffing up and getting more drag for our satellite. So that makes perfect sense. So here, change in magnesium 2 index, so more ultraviolet emission, and then a little bit later, a change in dA by dt. So as I mentioned, there seems to be evidence for causal relationships here for these guys, not for the others. And so some space weather events seem to affect CUAVA-1's orbit. What about the periodicity of about 25 days? Well, the sun's rotation period at the equator is approximately 26 days. So this is not inconsistent with active regions on the sun that are persistent, rotating into view and giving us a periodic increase in ultraviolet emission and X-rays, which then leads to puffing up of the atmosphere and increased drag. So on one hand, if you look at the analysis, the preliminary analysis that we did, it all looks quite rosy, really, quite positive, that some solar activity drives changes in the atmosphere that puff it up, because of heating, etc., and cause changes in the drag on spacecraft and thereby change the orbit, but that others don't. more formally, our conclusions are perhaps a little bit more nuanced. Yes, this is a relatively quiet period before we get to solar maximum, which people are arguing at the moment whether it's occurred just now in the last few months or whether it's expected in 2 years. But we had a pretty quiet period, so we might hope that that was a good period to disentangle the effects of the ultraviolet and X-ray emission near to the subsolar region from the effects of DST or KP, which are mostly associated with auroral activity and changes in the polar regions, which might then lead to puffing up of the atmosphere there. So it's a good period, good spacecraft to use. The data seem nice. Our analysis is ongoing, though. We were pretty happy with the preliminary results. And then I started worrying about the zero padding. And so Tony and I have been reanalyzing things, and now things are equivocal at the moment. But I think at the moment, our conclusion is, at least some of the time, it seems as though variations in the orbit of CUAVA 1, in particular the changes in the altitude, seem to be related to particular space weather events associated with solar ultraviolet and X-ray emissions, but not the geomagnetic activity. And the interpretation there is a simple one, that the ultraviolet and X-ray emission heats and ionizes the atmosphere, causes it to expand upwards. Our satellite then moves along, sees a denser region, has more drag, decreases its altitude more quickly than it would have. But that's not the case for the F10.7 centimeter radio flux, DST, and KP, which in the preliminary analysis don't seem to drive orbital changes for CUAVA 1. That's where we are at the moment. Preliminary results are really quite interesting. And we're hoping that with the refined analysis that we're doing, once we have everything correct, we will be able to be definitive about whether or not there's evidence for solar ultraviolet and X-ray emission and or the other forms of space weather affecting the orbit of our satellite. At the moment, there's weak evidence that that's the case, and we look forward to talking to you more about it in the future. But in general, people consider this event to be really quite interesting and exciting. I presented it for us at the Asia Oceania Geosciences Society meeting 2 weeks ago now, and it was considered novel and unique. So we're looking forward to finishing our analysis and presenting it. Thank you, and I'm sorry we've probably been a bit too technical and or a bit too equivocal. But happy to answer questions and so on from people.
Yeah, okay, thanks very much, Iver and Tony. Yes, so just one thing I wanted to check on with you, some misunderstanding. So basically the sun itself rotates, and it seems to have a cycle of about 25 days, and that's where you're getting some of the effects that is showing on the graphs there. Is that correct?
Absolutely true. Yep.
It's important to remember also, Wayne, that the sun isn't solid. It's a blob of fluid. And so the equator actually rotates more quickly than other parts of the sun.
Well, the key things to note about the talk is that I would guarantee a lot of people don't understand that, but you folks obviously do. But that's the important thing that we need. What we're trying to get out of that is the effect of the sun on the data there, and that's the reason why you've got that obviously showing there. The other thing to note is you're trying to work out which particular solar effects would be causing the drag to occur, right. And it seems to be that you are
specifically which measurements that we can use to predict
Right, which
of
is
solar activity affects spacecraft. Yeah.
when you said novel, obviously means that not too many people have tried to do this before, which is probably a pity in some ways, because we should understand a bit more about how this thing is affecting spacecraft.
It's really only
Well,
spacecraft.
exactly.
I thought.
Exactly. So it would be lovely to be able to, observe a change in the solar ultraviolet emission and then say, spacecraft operators, you should expect, your satellites in these particular regions to experience an increased drag effect of approximately this amount. And
There has already been one fairly catastrophic event when the early days when there was a whole bunch of Starlink satellites launched just before a solar event, and quite a few of them deorbited straight away. I can't remember. It was 25 or
February. It was in February 2022, and so that was approximately 3 months, 4 months. So that's round about in here, and you look at this. And there's really nothing much happening for CUAVA 1 at 400 kilometers altitude. And this is one of the interesting things, because CUAVA 1's at 400 kilometers altitude roughly. But the Starlink satellites that you're referring to were approximately at 200 kilometers altitude. And because they were deliberately injected low, so that they could then be acquired. And if they weren't acquired, they would deorbit quickly. But if they were acquired and commissioned, then they'd turn on their thrusters and they'd boost up. And so it was a good way, from Starlink's point of view, of quickly deciding to deorbit or let burn or re-enter their satellites, versus put the effort into the ones that were alive. So interestingly, CUAVA 1's data show not much effect around about the time of the Starlinks, but the Starlinks were significantly affected. And one of the things at AOGS that I heard on the Monday, so the first day of the conference, was that certain atmospheric ionospheric models predict a major effect at roughly 200 kilometers altitude, but none at about 400 kilometers altitude. And that's not inconsistent with our results here for CUAVA 1.
Well, the significance, thinking about it also, Iver, is that because your satellite was released near the space station, and that's where it's out, that's the major thing that they were always concerned about, was the space station's orbit being, if it's too low, it's a major problem with drag. And that actually proved that to a degree too with what you're getting. I mean, admittedly, your satellite's a lot different shape to the space station, but it's the same things, proving that the lower down you are, the bigger problems you're going to have.
Yeah, well, with the space station too,
more subtle than that.
Yeah,
because radiation is absorbed at different altitudes. Most of it's significant, well, a lot of it's significantly lower than us. Of course, you have the certain ultraviolet emission, which is absorbed by the ozone layer. And then there's, I guess it's higher frequency, which is absorbed higher up, and so on and so on. So there actually is good reason to predict that certain emissions will be absorbed preferentially low down rather than high up.
That's true, and that's the distance. So that's the interesting thing about it. But they also probably suggest that we have to try and do tests of different orbits as well.
Yes,
and inclinations too, if you can, but obviously that's not always possible.
That's true. Inclination could be quite interesting. Yeah, CUAVA 1's sort of 42 degrees inclined, just like the space station. Whereas I actually don't know the orbits of the inclinations of the Starlinks, but I think they're pretty much polar.
Yeah, well, that's the interesting thing. Polar orbits, nobody's got any data on that. It'd be nice to get some data on it. But
But they will all, in other words, I mean, the thing about them is they'll go through all latitudes then.
Yeah.
Whereas our ones will only be restricted to plus or minus 42 degrees for CUAVA 1. CUAVA 2 will be a polar satellite, essentially.
Right. So that's the new one that you'll be launching sometime in the next few months. Okay.
Something else that we noticed also, Wayne, we haven't presented here, is that as we see spacecraft getting down into very, very low altitudes, we see larger fluctuations in the velocity.
Yeah.
Just as you would expect, and it starts to look like turbulence. You can begin to see turbulence in the upper atmosphere.
Well, that does make sense when you think about it, because there's all issues about when does the atmosphere begin, but of course you're going to have still some molecules.
It's much higher than 400 kilometers.
Yes.
The ionized part of the atmosphere doesn't dominate until approximately until after 400 kilometers height, so it's higher than that.
Okay.
It's predominantly neutral even at the space station altitude of 420 odd kilometers, which is interesting.
Can I just make a comment? I haven't got a question, but it's more just a comment. You mentioned the Lom-Scargill periodigram.
Yes.
Now, EB and John and Ken's already gone, but that name should be very familiar to you. It's our one and very own Nick Lom.
It is. That's true.
It's in Skywatchers, yeah, the vice.
He was responsible for creating it.
Yes.
He was. Yes, him and Scargill.
Yes.
This is, in fact, it's the that there's a paper that they wrote, and it's got huge number of citations.
Oh, that's good.
Yes.
Yeah, which would be only
close.
something that Nick could work out, because he's quite right.
Thanks, EC, for telling us that. Yeah.
Yeah, sorry, I forgot to mention that, but yes, that's Nick Lom.
Yeah.
Yeah. Yeah.
And yeah, quite a novel contribution.
I suppose the interesting thing about what you're going to be doing is that if you're able to get some data on this and create it, you said that you were using NORAD data, was it? Or
yes, that's correct. Yes. Yeah.
So if that means that it's available for your satellite, you could pick others if you really wish to apply.
Oh, there's hundreds we could pick, Wayne. Yeah, it's best to use satellites with simple shapes because they've got a simple drag profile. If you use a complex shape, and we've tried this with the space station, that derivative, that DADT curve, which has the little spikes in it, looks like a forest. You know, it really is. It's impossible to suck any worthwhile information out of it.
Well, actually, that's not as silly as it sounds. Was in fact, you've got a couple of things pointing in other directions. It's almost like four trees point. It's the space station shape. Thinking about it.
Yeah, well, it's not just that, but they're also changing the angle of the solar arrays, which is the biggest drag. Whenever it's in insolation, of course, when it's in eclipse, they feather them. So it actually reduces the drag. So
really changing to try and maximize the energy. That's
right. And they've got to boost it every 30 or 40 days as it is. So this is why.
Which is why we wanted to not use the ISS. But it's also why we looked at Starlink, for instance, and a number of other satellites. And that was work that the student James Lee that I mentioned at the beginning, that he did more on that, but we haven't yet gone back and reevaluated certain aspects of his work. We expect, though, we've got the same zero padding issue, but broadly speaking, we expect very similar results when we redo it. But one of the underlying qualitative ideas was that if we looked at the TLEs for multiple different satellites at different altitudes, then we'd be able to get a picture of the drag as a function of time of multiple satellites through different heights, and really demonstrate that there is a significant difference in where the ultraviolet and X-ray, et cetera, emission is absorbed, and where that starts puffing up the atmosphere. Maybe it starts low down. Well, we think it starts low down and then expands out. But for those emissions, but if it was due to energetic particles in the auroral zone, we might expect that to happen at larger heights and then move down. So that sort of analysis that you alluded to is definitely of interest to us.
We can have a bit of fun testing it, because a couple of things I can think of immediately is polar orbits and also fairly circular. So those are the different types that you can once you get the numbers, the algorithm worked out, you can test it on that. But as you said, you need to make sure you pick objects which are the right shape, otherwise it's not really useful.
So it's just the simplest shape we can. Yeah.
It's ideal, but I guess you work with what you have.
Well, yeah, that's the size of the CubeSat. You don't want anything too different to that shape, I suppose. Otherwise, it's too complicated to put the numbers into it. Yeah.
Well, just as long as the frontal area doesn't change too much in the course of the flight.
Right.
So if the frontal area changes because it's, say, tumbling,
yes,
and we see changes in the drag and we see changes in the altitude more.
We would expect to.
Yeah.
And it's worthwhile mentioning that CUAVA 1 is believed to have been tumbling all the time.
Okay.
And we don't know why. Because it really should have started to align with the velocity vector. Usually what you expect is that a satellite, satellite would be if it's going this way, then it will align so that its long axis is parallel to the velocity vector. It won't try and go like that. Instead, it will shift to being like that just because of drag. The argument being that if it's like this, just a slight bit away, there's slightly more drag here than here, so it rotates like this until it's like this, and now it's symmetric. So we would have expected CUAVA 1 to be to rapidly stabilize, within a month or so. But there's evidence from optical instrument measurements, as in people taking pictures of it, that it was tumbling still.
So it sounds like we'll be able to do some of this measurements on CUAVA 2 when it launches, but obviously you're saying that that orbit's going to be quite different. So that will be a good way of looking at it.
Mm-hmm. It will be, yes. We should be able to do it on Waratah as well. And in fact, there are many satellites whose TLE data are published by NORAD or Celestrak more directly. And so this is the sort of thing that one really can envisage doing as a function of time and as a function of altitude and of latitude as well.
Yeah, so it's just a matter of really picking out the correct ones to probably try and put it through based on your knowledge of what the satellite, how the satellite is shaped.
And there's something like 20,000 objects that we can chase, even things like rocket bodies and things like that.
Yeah, I know. I think it's just all a matter of working through and picking the right ones to do your tests on, and then you'll get some decent data out of it. You can at least be
That's the hope. That's the hope. Just as a matter of interest, though, how fast do people here think that information about a heating event should travel in the atmosphere? What sort of speed do you think that would correspond to? If you've got a sudden heating event here, how fast would information about that propagate? This is a trick question, by the way. How fast do you think it would be, or what would that speed be?
Still think we're talking about seconds, aren't we?
Well, what you're talking about is this characteristic speed at which things move, which should be about the thermal speed of the particles, or actually close to the sound speed. And so the sound speed's of order a kilometer a second down here. And, but the temperature's, that's at about 400 degrees Kelvin. And even if it's 1,000 degrees, it only the speed only goes as the square root of the temperature. So you still expect something which is, less than 10 kilometers a second. But if you're looking at an altitude of 400 kilometers at 10 kilometers a second, that's only 40 seconds, a minute or so. So these heating events really should be dramatic. The information should propagate very quickly upwards. So I'm actually surprised that we have any that everything isn't at 0 days. All of the lags aren't zero, that we're not seeing instantaneous events.
Oh, okay. So you're worried about, that's why you're worried about that offset.
I'm worried, yes. I've got a theoretical reason for being worried about it, and also, well, a couple of them. But it makes it very interesting, because often we do seem to see evidence of this, of these correlations between the changes in the orbit, dA by dt, and changes in, for instance, the ultraviolet emission. And it's, they seem well correlated by eye.
So that's why I'm thinking that maybe doing it on a satellite with a totally different orbit might give you a better idea of whether how closely it matches.
That's possibly true.
And a range of altitudes. That's a big one.
So that's why they're interesting. Most people don't, unfortunately for us, most people don't like equatorial orbits, for instance. It's mostly space station type orbits, so it's 42 degrees or so, and polar orbits.
Equatorial is really not easy to do anyway. If you look at where the launch sites are, you're going to have a launch site virtually around Singapore, and then you've got to justify where you're going to put and a lot of, for good other reasons, that they want to put satellites over as much land coverage as possible. Something that just sits around that part of the world doesn't really interest some people unless you're probably using the data directly off it. And you know what I mean by
communication satellites are always directly over the equator because they've got to be some geostationary.
But they're in a totally different location, a long way up.
Yeah, 36,000 kilometers. Yeah,
that's exactly right. You're not going to be doing any measurements and stuff like that because
unless there's a compelling reason to put them in an equatorial orbit, you wouldn't do it. Yes.
Yeah, I'm just thinking of the type of ones that you're doing at the moment, though. The ones that are equatorial are in different, long way out, and they're doing the measurements on that is, well,
it wouldn't be meaningful for the atmosphere.
And to get anything useful for the atmosphere because they're too far out. So that's exactly right. So anyway, but that's great in terms of what you're doing. But you'll have to give us an update sometime in the future if you can get it going with that.
Yeah, we will try.
Maybe in another 12 months or something after you've done some more refinement.
Well, I hope it's a lot less than 12 months. Well, I can imagine that another talk might be at least 12 months, but I hope that our analyses will be finished within less than 12 months.
You're able to do that, but then again, it's another talk, isn't it, really, in terms of that, an update talk on it. So, okay. Have you got any more questions, or have you kind of done most of the speak now, folks? I'd like to thank you very much for the talk.